Hello, everyone, and welcome back to Qubit by Qubit. I hope you had an enjoyable break, at least from this course. I don't know how much of a break it was in other aspects of your life, but yeah, we've been off for 2 weeks now. Hopefully you haven't forgotten everything because we are going to jump right back into some new quantum computing content. This lab is going to be all about randomized benchmarking. So I know that in the lecture, I guess just a couple of days ago, Amir discussed randomized benchmarking. He also talked about some physical, implementations of quantum computers. We'll touch briefly on the physical implementations part, but mostly spend today talking about randomized benchmarking. So let's get right into it. The quick program for today, in case you have forgotten what these labs normally look like, we'll start off with the Canvas attendance quiz. We'll have our pre-lab Zoom feedback. We'll do our lab content, and then we'll do our post-lab feedback. We don't have any sort of questions from last week because last week was 3 weeks ago, and we are just going to kind of be starting fresh from this point on. The Canvas attendance quiz, we are in lab number 1, as usual, and the quiz password today is 8437. The question is, do you agree or disagree with the following statement? This course provides enough resources to answer my questions about the content. For example, Piazza, office hours, homework review sessions, etc. And then there's an optional part of this that says what additional resources would be helpful. So here we're just trying to gauge, we're running this course online, which is a first for many of us. It's a little bit of a weird format, as I'm sure all of you have seen in the past year. But yeah, we want to know how well supported you feel between these different resources we've given out. That question about additional resources, it is totally optional. If you don't want to fill it out and you go to submit the quiz, I believe it will give you a warning that's like, hey, you're submitting without answering this question. Don't worry about that. This question is optional. You can just click through the warning and you'll still get the marks for the attendance. Just make sure that you fill out that first question. Do you disagree or agree with that following statement? Okay, let's go on to the pre-lab Zoom feedback then. Or actually, I'll just open up the chat in case anybody has any issues with the attendance quiz or any questions. But let's pop up the pre-lab Zoom feedback to see how people are feeling this week about various quantum computing physical systems and randomized benchmarking. In the meantime, anybody have fun stories or anecdotes from their break? Anything interesting you did? I'm almost done my undergrad degree program, so that was my interesting thing. I've been writing exams and final assignments and stuff for the past 2 weeks, but I am close to the end, so that's exciting. Didn't I finish undergrad? I wish. I'm in my very last term of my undergrad, so almost done. I don't know who that person is, but that sounds awesome. Hopefully. I don't know who they are, but yeah, all my courses have been online as well. I guess that's why I was mentioning just this online format has been weird to get used to teaching, also very weird to get used to being taught. So somebody asks if we can go into quantum volume a little bit today. I actually, to be totally, I can give you the 4-sentence version of what quantum volume is. I'm not really familiar with any of the specific calculations beyond that, so I'm not sure how much more detail I could actually get into. But I'm happy to follow up with some resources in my follow-up post if you're interested. Okay, cool. So most people have voted in the pre-lab poll. I will go ahead and share those results just so everyone sees where we're at. So I would say this is generally lower than what we've seen in previous labs, which, to be honest, is pretty understandable. I think one of the themes that you'll see, well, you started to see even with the algorithms we went over before the break, but a theme you'll continue to see is that we're going to be sort of giving you like high-level introductions to all these various topics in quantum computing, whether it's algorithms like Grover search or randomized benchmarking, and some stuff in the coming weeks as well. We literally don't have time to get into like the nitty-gritty details of it. And so it might not feel like, you could sit down and rediscover these algorithms or techniques on your own. But what we're hoping is to give you the general idea of how they work and so the intuition behind them. And so that's what we're going to be doing today as well. All right, the quick agenda for today, as I said, is going to be mostly about randomized benchmarking. We'll start off with a quick discussion of some physical implementations of quantum computers and the errors in them. Then we'll talk about various strategies of dealing with errors. And then in the last two sections here, we will talk about this particular technique called randomized benchmarking, often abbreviated as RB. We'll talk about the specific steps in RB, and then we'll hop over to the IBM quantum experience in the last like 15, 20 minutes of the lab to actually show how you code this thing. Okay, so as I said, let's begin by talking about some physical quantum computing systems. You should have already seen a little bit of this in the lecture. Here are an assortment of 4 fairly common quantum computing systems. There are, of course, others besides this. But yeah, superconducting qubits, trapped ion qubits, photonics, diamond and V centers. The one I work on is neutral atoms, and there's probably many more beyond that that I'm not aware of. So there's all of these different possibilities. And often when I tell people what I do, one of the things I have to start out with is what I'm actually working with. Because a lot of people might be familiar with quantum computing, but they might not realize just how many different types of quantum computers there are that are currently being researched. So the reason that there's all these different quantum computers out there is because at this point in the development of quantum computing, we're just not sure which ones have the best performance for different types of applications. So the analogy I like to use is that, way back in the 1940s or around then, when we were coming up with the model for computers, we didn't necessarily know how they were going to be built. Today, we take it for granted that you use silicon microchips and you're going to be passing electrons around on those microchips to do computations. And we've sort of converged on that as the best implementation for a classical computer. Probably the closest to that would be superconducting in the quantum computing world, although it is very, very different, just to be clear. But there are all of these other possibilities for how you could do quantum computation. You can use different materials. Your computation units don't have to be electrons. They can be atoms, they can be photons. And each of these has different pros and cons. And so a research team studying any of these individual types of quantum computers will probably be able to tell you why they think theirs is the best. But the reality is that there's really no consensus. Each of them has good sides and bad sides. And it's a continuing area of study to find out which are the best for which applications. That's very high level, but one particular metric that we often care about quite a bit is errors, right? So again, this is something you might not think about very much in classical computers because, when you do something on your computer, you're usually expecting it to do what you say. You're not expecting that clicking a button will only succeed 90% of the time, right? But with the current state of development with quantum computers, the error rates are often very high. So something like a 90% success rate would actually be reasonable, right? Or to say it a bit more pessimistically, a 10% failure rate. So we tend to care a lot about, how many errors happen on these different kinds of computers, but also what types of errors, how those errors manifest, how we can get around those errors, et cetera, et cetera. So there's a whole study of error characterization on these different systems. And that's what we're going to get into a bit today. Okay, so we have already seen errors in quantum systems before. So I'm going to start off with a Zoom poll, get you back in the zone of thinking on your own a little bit, and ask you the following question. These are 2 histogram outputs from executions of Grover search. So remember, Grover search was supposed to tell us where is Waldo. We know that Waldo was in the 4th position, and so the answer should always be 1, 1. Now, can you tell me which of these was run on an actual quantum computer and which was run on a simulator? I'm going to pop up a Zoom poll so you can enter your answer there. And you'll notice that there's also a second question here, which is a follow-up. Why did you give the answer you gave? So I'm going to give a few seconds here for everybody to fill in their answers. Hopefully the first question is fairly quick. The second one, why you gave that answer, might take a little bit longer to think about. So once 50% of people have answered, I will go into my thinking on this question. Okay, so about half of you have answered on this. So I'm actually going to kind of flip it around. I'll talk about the why first, and then hopefully once we answer the why question, it'll be obvious why the answer to question 1 is what it is. So there were 4 possibilities given in the poll. The first one was that a real quantum computer only gives 1 result. So this is kind of intentionally supposed to be a trick answer, because it's true that when you measure a quantum computer, you're only going to get 1 result. But remember, usually when we execute something like Grover search, we provide that argument in Qiskit that's like shots equals 1,000 or something like that. And that means that you run the computation 1,000 different times. So even though each individual execution only gives you 1 result, the aggregate of all of them gives you some probability distribution, like we see here. So that one is not the answer. The second one is that a real quantum computer has some error. And then I guess it's cut off on my screen, but a real quantum computer has some error. This one is definitely true, right? I just went over this, that quantum computers have often pretty high error rates, especially relative to what we're used to. And so this would be a valid reason for seeing imperfect results on a real quantum computer. The third one is that a simulator uses classical randomness to simulate error. This is also kind of a trick, because the simulator does use classical randomness, but only to collapse superpositions, right? So if you have a 50-50 superposition, it's going to use randomness to give you, one answer about 50% of the time and the other answer about 50% of the time. But so far, as we've learned it, the simulator does not do noise, right? If you prepare a 0-0 state, the simulator is always going to tell you that it's a 0-0 state. The final question here, or the final answer, sorry, was that a simulator computes the theoretical answer using linear algebra. That's actually also true. And so I guess you could have put it, or you might not have, because it's totally a true statement. It just doesn't really explain why you had the answer to the first question. So to recap, 2 and 4 are true. 1 and 3 were supposed to be kind of tricks. And if you take all of these into account, indeed, the actual quantum computer is choice B, because we see some error here, right? We know from Grover search that it should tell us the answer 1-1 with 100% probability. That's not what we see in choice B, because there is some error from the quantum computer. Okay, I will go ahead and share that. It seems like about 85% of you were on the same page with this, which is awesome. And if not, yeah, the point of this question was really to get back to the idea of errors in real quantum computers and simulators sort of creating the ideal perfect answer just by using linear algebra. Okay, so that's a quick review of the fact that that quantum computers have errors. I'm going to open up this question as well to the chat and ask you, what are all the different types of errors you can think of that might come out of a quantum computer? So this can be very general. You don't have to mention specifics necessarily, but hopefully you heard some different types of errors in the lecture on Sunday. And so, yeah, throw out in the chat some different types of errors on quantum computers that you can think of. One person says relaxation. Yes. Decoherence is a good one. Yep. So decoherence is a word you will hear a lot in quantum computing, for sure. The decoherence time. Yep. Okay, yes, phase shift. That's good. Sort of related to these other two. Anything else? Okay, someone says gate errors, amplitude errors. One more, readout error. Okay, perfect. Then I think I'll stop there because I'm running out of room. But yeah, all of these are totally valid sources of error, and all of them happen in slightly different ways for different types of quantum computers. And this is why the study of errors in quantum computing is actually, a whole field of study. There's a lot of different kinds of errors. For each of these different kinds of errors, you have to think about how do you characterize them, right? So what is a number or a set of numbers that you could use to describe the error? How do you measure that, right? How do you actually take a real quantum computer and derive some values for these errors? How do you interpret them? How do you compare them between quantum computers? I mean, there's a whole number of different questions about how you generally analyze these errors. So the three that I'll summarize here are sort of the highest level categories of errors, and you all already mentioned two of them. The first one, though, is sort of a more general category for a bunch of the ones mentioned. For example, relaxation, decoherence, phase shift as well, would all be characterized generally as Qubit errors. And that basically means that the physical system you're using to implement your qubits is going to have some error, right? So for example, if your qubit is an electron jumping between orbitals, right? So it can be in a really far out energy state, or it can be closer to the nucleus, then over time, your electron might decay, it might lose energy and go back to the nucleus, even though it started off further out, right? And that would be an example of a qubit error. So left to their own devices, qubits are not perfect. The second category was already mentioned, gate errors. And this is referring to any errors that are induced by a gate, right? So again, using an example, on an ion trap computer, you use laser pulses, right, to do gates. So if you wanted to do an H gate, that would be some kind of laser pulse. But that laser is not going to be perfect, right? Every real world instrument has some margins of error, and you might get something that's not exactly an H gate. And then if you had a circuit that had a lot of these, almost but not quite perfect H gates, that would build up over time into some error that you could see. And then the final category, which was also mentioned, is readout errors. And this refers to any error that happens at the measurement stage, right? So even assuming that your quantum computer was perfect, there were no errors in the qubits, no errors in the gates, maybe there are still some errors in the way that you measure your quantum states and the way that the state collapse works, right? You might notice, by the way, that these three things basically correspond to the three sections of quantum computation that we've been talking about: the initialization, the computation, and the output, right? And so this is, a fancy way of saying that errors can happen literally anywhere in your circuit. And when you're implementing things in an actual lab, you have to think about all of these things and consider what effects they might have. Somebody asks, in which category will noise be categorized? I think it would usually be categorized under qubit errors, because environmental noise will just cause your qubits to lose their exact state over time. But theoretically speaking, I mean, environmental noise could affect any of these, right? I think usually you would put it under qubit errors, but these are not, strict categorizations. They're just some high level ideas to get you thinking about all the different ways things can go wrong, which I guess is kind of pessimistic. Yes, exactly. Noise is more of an environmentally induced error, right? And so just to give a concrete example of that, I guess, again, going back to this example of atoms, I will use atoms a lot just because that's what I work with. But atoms are very sensitive to temperature, right? You might know from a chemistry or a physics class that temperature, what we think of as heat, is really just the kinetic energy of atoms sort of vibrating around, right? And you can, this is probably not an accurate picture 100%, but you can think of it as, if your atoms are shaking around too much, they will literally sort of shake and randomize their own quantum state, right? The only way to have a qubit that stays perfect for infinite time is if it was at absolute zero, if there was no kinetic energy in that qubit, and that is impossible. So we're always going to have some errors. So right now, the status of quantum computing is the following. We have quantum computers with roughly tens of qubits. So all I mean by this is that the largest ones that are coming out in the near horizon are going to be on the order of sort of 60 to 70 qubits, probably. And then obviously we have ones that are less than that. We don't really have any that are into the hundreds or many hundreds of qubits. One asterisk I will put here, you might have heard of a company called D-Wave that creates quantum computers with thousands of qubits. The short answer there is that their definition of qubit is not quite the same as ours. And so I'll generally ignore that discussion for now. But for the types of qubits we've been talking about in this course, the most we have on any physical systems, as far as we know, are tens of qubits. And crucially, these quantum computers that we have today are quite noisy. So as I said before, they can have error rates of like 10%, right? Which is, and of course, lower error rates as well. But generally speaking, errors are a big problem with today's quantum computers. There's a few different ways we can try and deal with errors. And again, this is a very rough categorization, but it's helpful to think about all the different approaches that you could take. The first is simply to characterize errors. And maybe I shouldn't say simply, because all of the stuff I've been mentioning up till now about all these different types of errors to consider, how you measure them, how you assign them to numbers, how you compare them between different computers, all that stuff falls into this category of just characterizing errors, right? The least we can do is at least try to understand why these errors are happening and how we can measure them, right? And so it says here, difficulty level easy. Of course, all things are relative. This is an active area of research, so I wouldn't call it easy in a traditional sense. But characterizing errors is at least easy compared to what we're going to get to. Number 2 on this list is mitigating errors, and we'll call this difficulty level medium. Mitigating errors means that you are not only categorizing your errors, but you're also making modifications to your algorithms that are going to make them less susceptible to error, right? So there's a great example of one error mitigation technique in the Qiskit textbook, if you're interested in the details. But what it usually involves is looking at your error characterization, right? So it requires this first step, and figuring out what that means about the ultimate measurements you'll see, right? So you understand the errors well enough to know how it's going to affect your algorithm, and then you take that into account in your final analysis. So this is a little bit more difficult because somehow you need to figure out how to extract the real answer, even among all of this error that was introduced in the system. Next level up is what we'll call hard difficulty, and that is to correct errors, right? So error correction is another huge area of research, and that is taking active steps inside your algorithm itself to undo errors at various points, right? So maybe like 10% of the way through your algorithm, you'll insert some special circuit that undoes all of the errors that have accumulated up to that point. And then you do the next 10%, you fix all the errors again, you do the next 10%, you fix all the errors again. This is really hard because, in the error mitigation, it's up to you as the human looking at the results to somehow figure out how the errors might have affected them and kind of reverse engineer what the real answer was. In error correction, you're trying to design a quantum circuit that does that for you. And that is, again, a significant step up in terms of difficulty. And then the final layer here, which I guess is a bit of a theoretical novelty, is to prevent errors. And the difficulty level here is super hard, if not impossible, right? Certainly for some kinds of quantum computers, it's not clear at all how you would ever prevent errors. And so, I mean, as far as I'm aware, there's not really people who are seriously looking into how to prevent errors. All research pretty much falls into these first 3 categories because preventing errors, as far as we know, would be very, very hard. So let's talk a little bit more about the subject of characterizing errors. And we are going to look at the game of telephone. Some of you might have heard this game, some of you might not have, so I'll do a very quick sort of summary here. Basically, the way it works is you have one person who has a message, right? So in this case, the individual on the left here has a message peas, right? They whisper this to one person. That person tries to hear what was said, but they're only allowed to say the message once, right? So it's possible that this person mishears and thinks that the message was bees, right? And then they're going to whisper this to someone else, and you carry on this chain of transmission until the very end. And oftentimes the result you get at the other end is nowhere close to the message that you started with. And so as you can imagine, the more sort of links in this chain you have, the more garbled your message is going to get, right? If you only had the 5 people, like in this picture, maybe you can get to something that's relatively close. But if you played this game with like 20 people in a line, things can go wrong very fast, right? So this is actually not a bad way to think about characterizing errors in quantum computers either. So let's do another quick Zoom poll. This is going to work the same way as the last one, where we have an initial question, and then I'll also get you to fill out some why responses to that question. So we have 4 circuits here. I am drawing them fairly small. The exact gates in these circuits don't matter, so don't worry if you can't see them too well. But there's the first circuit. Second circuit gets a bit bigger. Third circuit is here. And by the way, the 2 lines here is just a continuation, right? So if we tried to draw them all on the same line, it would be too long. So it just kind of wraps around like this, okay? And then same thing here for the 4th circuit. So the question, which circuit do you expect to have the most errors? I will, oops, that's not what I meant to do. I will go ahead and throw up a Zoom poll on your screen right now. Tell me which one you expect to have more errors, and then also tell me why. As before, I will start answering this once 50% of people have given their responses. I guess in the meantime, just to answer some of the questions in the chat, one person asks, do superconducting quantum computers give the least errors? I don't know that you could make such a general statement. I am not familiar enough with superconducting computers to get into the details of exactly what types of errors they're susceptible to. But the general, I guess a general statement you can make is that different implementations will have trade-offs, right? So even if you have an implementation that has relatively low error rates, error, the thing we're talking about in this whole lab, is itself only one, characterization that you might consider, right? And so you can also look at what quantum computers, have the fastest execution time, which are the cheapest to manufacture, right? Those kinds of questions. And so oftentimes there's going to be trade-offs. As far as I know, superconducting qubits are quite good. That's why a lot of companies are investigating them right now. They seem very promising for a variety of reasons. I'm not sure if errors is one of those reasons, but I wouldn't be surprised. Is error mitigation and correction what Q control is doing? I'm not very familiar with Q control. You all have probably heard of more quantum computing companies than I have, so I'm not sure on that one. And then somebody made a statement about D-Wave in a little bit more detail. This is exactly correct. So I won't go into the details, like I said, on D-Wave, but suffice it to say that their computers work quite differently than the ones that we're looking at. Okay, let's look at the answers to this poll then. Just like before, I'll go over the whys first. So the first response was that shorter circuits, I guess the first two kind of go together. Shorter circuits have more errors, or longer circuits have more errors. Most of you got the correct answer here, which is that longer circuits have more errors, right? And the intuition behind this is exactly like the game of telephone. Each individual gate has some chance of introducing errors. And so if you have a huge line of gates, like option D here, there's a much higher chance that errors are going to be introduced. The second two options were about barriers, right? So one was circuits with more barriers have fewer errors, and then another was that circuits with more barriers have more errors. At least as far as we are concerned, barriers don't have any bearing on error. right? So barriers are just a visual thing for our purposes. And you'll see that these circuits indeed, choice D has more barriers. That doesn't have anything to do with the error rate though. The only reason that, well, I guess I'm giving away the answer to question 1, but the only reason that D has more errors than the rest of them is because it has more gates. So question D was the correct response for the first part. Yeah, and I guess just to clarify as well on the barriers, they do have a meaning within Qiskit that is beyond purely visual, just to be accurate with my speech here. But it has nothing to do with the error rate. We're going to use them mostly just for visuals. Okay, one more Zoom poll. This one is a little bit more challenging, and it dips into some of the things that you heard in the lecture that I have not necessarily covered here. So I'm happy to explain more afterward, though. These are 2 quantum computers that we are going to investigate in the IBM quantum experience in just a few minutes, IBM Q Yorktown and IBM Q Belem. Which of these computers do you think will have fewer errors? Now, if I just gave you the computer names, that would be a really unfair question. So instead, I'm giving you some information about the computers here. So you can see the layout of the qubits, right? So each of them is a 5-qubit system, so there's no difference there. And then we're also giving you some stats, right? The average C0, average readout error, and then average T1 and T2. Just like before, there is an initial question here, which do you think will have fewer errors? And then there's a why question. And the why question here might be a little bit more difficult, but think about it, give your response, and then I will talk about it in more detail once 50% of people have answered. So someone asked in the chat, what are T1 and T2? I will go over that briefly after we answer this question. One hint I will give, there's enough information here to answer the question without looking at T1 and T2, but we will talk briefly about it. The US is microseconds. Yeah, exactly. Okay, so about 50% of you have voted at this point. So I'll talk about the first 2 choices in the Y section first. And this was to do with the average error, right? So both CNOT and readout error. And the question was, does lower average error mean fewer errors, or does higher average error mean fewer errors? Even if you don't know exactly what these calculations are, these average CNOT and average readout errors, hopefully you can intuit a little bit that a lower average error rate would mean fewer errors total, right? And so here, the error rates are actually pretty close, but you can see this one is roughly 2.7 versus 2.4 on Belem. And then we have 6.9 versus about 3.7, 3.6, 3.7 on Belem. And so in both cases, Belem has the lower error rate. And indeed, that does mean that on average, there will be fewer errors on Belem. So their lower average CNOT or readout error means fewer errors. And that is a justification for why Belem will have fewer errors. We can also look at T1 and T2 though. This one's a little bit tricky because you have to remember what T1 and T2 are measuring, right? This is the time it takes for relaxation or decoherence, respectively. And I won't spend time now talking more about what those things are. My understanding is they were covered to some extent in the lecture, but suffice it to say that this is, the time it takes for your qubits to get garbled and scrambled, right? And so actually, it's better if you have a longer time here. because think about it this way. If I had a decoherence time, for example, of 10 seconds, that means I can leave my qubits sitting around for 10 seconds before they get garbled and randomized, right? Versus something that only has 1 second decoherence time, that means it gets garbled way faster, and that's not good, right? So T1 and T2, you actually want higher numbers because that means that your qubits stay in a good state for longer. Okay, so somebody in the chat asked about the shapes here. I will spend a minute or so discussing the shapes because I think that is an important feature here. So you might be wondering, okay, we have these two quantum computers. Belem seems to be better in all respects, right? The average errors are both better. The T1 and T2 are both higher. And so in theory, it should be better in every way. Why don't we just always use Belem? Why do we have any use for Yorktown? Well, that difference comes down to the pictures here. So the pictures here are meant as graphical representations of which qubits can have 2 qubit gates performed on them. Okay, so for example, if I wanted to perform a C0 gate, which we know is a 2 qubit gate, between qubits 0 and 1, I can do that directly. There is a laser inside the Belem computer that will do a C0 between 0 and 1 with 1 pulse, right? No, well, maybe not 1 pulse, but it'll do a C0 between 0 and 1 with no further steps involved. But let's say instead I wanted to do a C0 between 0 and 4. In this case, because these two are not linked in this diagram, we can't directly do that. And so what you would do instead is you would use swap gates. You would swap 3 and 4 to move qubit 4 into this location. And then you would swap qubits 1 and 3 to move qubit 4 to this location. Then you would do a C0 between these two. Then you would do the swaps again to move qubit 4 back up to location 4. So as you can see, that's 5 gates to do a single C0 between qubits 0 and 4, right? Which is not very good. That's 5 times more complicated than it needs to be. So something like Yorktown has more of these interqubit connections, right? In this case, there are 6 possible pairs of qubits you can do gates between, while on Belem, there are only 4 possible pairs. And so you could do more flexible algorithms that do C0 gates between more pairs of qubits, possibly faster and more easily on Yorktown, even though it has higher error rates. So generally speaking, having more connectivity between your qubits is a good thing, right? And so that's where the trade-off comes in here. Yes, Belem has fewer errors, but that comes at the cost of having less connectivity between your qubits. And so you have to get into this business of swapping things around and moving your qubits if you want to do certain C0s. Hopefully that makes some sense. So somebody asks, are swaps handled by the compiler, or do you need to manage them yourself in Qiskit? That's a good question. I'm actually not sure. I wouldn't be surprised if it was done by the compiler because it's fairly straightforward to do. But it definitely adds a lot of complexity to your algorithm if you're doing a lot of non-connected C0 gates. Okay, could you repeat how the gates are used on Belem for connectivity? So the lines on these connectivity diagrams are just referring to which qubits can be can have a 2 qubit gate executed on them, right? That's all these little connections are saying here. Oftentimes these diagrams are somewhat physically motivated, right? So if you actually looked at the ions, if these were ion computers, which they're not, they're superconducting qubits. But if these were ion traps, for example, you might look inside the computer and see that the ions are literally physically laid out like this, right? That's fairly common. But for superconducting qubits, it doesn't necessarily have to be that way. These are just good ways to think about the various ways connectivity can happen. Oh, someone said I skipped their question. So somebody asks, if the gate C0 error is 10 to the minus 2, right, like it is here, does that mean that every 100 gate C0 operations will have different than a C0 or it won't operate at all? So the The definition of the C0 error is a little bit involved. I think, well, I mean, it's not something you couldn't learn. I just won't go into the details of it right now. A good way to think about this is, well, I guess one way you could think about it, which is going to be a roughly good approximation, is if you did, if you had a whole bunch of circuits that are starting off with 0, 0, 0, 1, 1, 0, 1, 1, and you pass these through a C0, right? We know what we expect in all these different cases. We should get the last two to swap, and then the first two should stay the same. But if you do this on a real quantum computer, of course, you won't always get this, right? And so what we could do as a simple measure is you could just take the proportion of runs that are successful, right? So what proportion of runs give you each of these values? That would be totally valid. It's not exactly how these average errors are calculated, but it's the general idea. So what you said here, where something with an error rate of 10 to the minus 2, you can think of it as, yeah, roughly 1 in 100 of these gates will just do something wrong. We're not specifying more exactly what that is, though. Okay, I'm going to stop on questions here just so I can keep going on the content, but I will be happy to answer a bunch of these in optional content. Okay, so yeah, I think I talked about this question enough. All right, now we get to the real subject of today's lab, which is this thing called randomized benchmarking. So randomized benchmarking is it's an actual sort of protocol, right? And as I said, it's often called RB. And we are going to use this particular technique to try and check our intuition about Yorktown and Belem. Now, the intuition behind this is actually very similar to what I just described with that C0 circuit, except now we're not going to be testing a C0 gate per se. We want to test the whole computer, as a whole, right? And it might not be clear exactly how to do that, but that's exactly what randomized benchmarking does for us. So this is what we're going to do. We're going to start off our circuit with all zeros, right? And so we'll start off our circuit with all zeros, but we're going to set up some circuit in the middle that should just be identity, right? So it should bring our message of all zeros, do a bunch of crazy stuff to it, but ultimately result in all zeros. We will then give this same circuit to both quantum computers and compare their performance. So we'll see how we do that, but basically it's going to look like what I just said, where you look at the, if I do 1,000 runs and 980 of them give me all zeros, then I mark that as a 980 out of 1,000 success rate. And you'll see how we do that in IBM Quantum Experience. Just the last note here, from the performance, you'll see that we create a graph once we get to the notebook. So from that performance graph, you can extract something called the gate fidelity. And the gate fidelity tends to be the standard measure well, it's one standard measure we use to quantify errors in quantum computers. Just if you hear that term, just know that it's very closely related to what we're doing here today. Okay, so general idea, we're going to start off in all zeros. We have some circuit that should just be identity, and then we're going to expect that we get all zeros at the end. Of course, we won't always, and so that's how we measure our success rate. The remaining question is, what does this circuit look like? Right? How do we come up with a circuit that is identity? Well, it's pretty easy to do by hand. You can just string together a circuit that is, sometimes we'll call this palindromic or mirrored. And it's mirrored just because if you read it, well, not including the measurements, right? If you just ignore the measurements for a second, reading it from the left gives you the same circuit as reading it from the right, right? And another way to think about this is if I draw a line down here, whatever this first circuit does, we are then going to invert it. We're going to apply the inverse for the second half of our circuit, right? And so you can see here that this circuit should just be identity. But because we're doing all these gates, and because our qubits are going to be in the system for some finite amount of time, and because we're measuring, we get qubit error, gate error, and readout error, all contributing to incorrect results. Now, generating these circuits by hand is fine, right? But as you'll see in a moment, for our purposes, we're going to want to generate circuits that are possibly hundreds of gates long. And so doing that by hand would get very tedious very fast. So luckily, Qiskit has a built-in function for this that's going to generate random circuits, for us. This function is called randomized benchmarking, so RB, seq, standing just for sequence, and it's in this library. Don't worry at all about the exact syntax here. The theme with the rest of this lab is going to be, don't worry too much about the code exactly. You can always look up more about what each individual argument and syntax piece means. That's not really the point, though. The point is to give you the idea of what's going on and to get some actual results. Okay, so here's some of the code that we're going to use. We will just import that function. And then the way that you call this is the following. It actually gives you two outputs. So one of them is going to be a 2D list of circuits. The reason this is 2D is because, well, we'll get into it in the notebook. I'll explain more about that. But yeah, it gives you the list of randomized circuits. The second parameter, we don't care about that, so we'll just call it underscore and forget it exists. The inputs to this function is one, a list of circuit lengths. So you will tell it, how long do I want my circuit to be? It's not quite the number of gates, which can be a little bit confusing. So even if I pass in a 1 for the length vector, it's not going to give me a circuit that just has one gate. But the details of that are not important. This is a rough measure for how long your circuit's going to be. So for example, I could pass it an array that's like 1, 5, 10. And in this case, it's going to give me a list of circuits. The first one is going to have, roughly 1-ish gates. The second one is going to be 5 times as large. And then the third one is going to be 10 times as large, right? And that's generally how this works. RB pattern is something we're not going to use too much, but we still have to specify it just so this function does what we want. It's the number and pattern of the qubits. You'll see what that means when we get to the notebook, though. It's actually fairly straightforward. Okay. So as I said, it would be really time consuming to, well, I guess, sorry, this is different. It would be really time consuming to run these circuits on actual quantum computers. So we are going to try and use a simulator. The problem here is that, as I said before, simulators, as we've learned them so far, don't have any noise, right? If you give them a theoretically ideal computation, they're going to give you a theoretically ideal answer. We don't want that here, though. We actually want to see the effects of noise. That's what we're trying to measure. And so in Qiskit, again, there's a function for this. We can add a noise model to the simulator. And this is going to make the simulator simulate a particular noise model. So this is how we do it. Step one, we're going to import noise model. You'll see the code for that when we get to the notebook. Then we are going to choose the particular quantum computer we want the noise to mimic. So in this case, we're going to mimic the noise of Belem. We then construct our noise model from that backend. So IBM has already gone and calculated exactly how the error works on Belem, and we're going to import all of that knowledge into our noise model. And finally, when we execute our job, you'll see, as usual, we have shots equals 1024. But now we have this new thing here that specifies we're going to use a particular noise model. And that's really the only addition. This will make our simulator simulate Belem's noise. Okay, so these next couple of slides before we hop over to the notebook are just some screenshots from the notebook. So I'll go over them fairly quickly because we will see them again. The first step, as I said, is going to be to create our noise model, right? And so in order to do that, we have to get a particular backend from IBM, and then we're going to load in all of their knowledge about the various errors that backend is susceptible to. Step two is we're going to use that randomized benchmarking sequence function to create randomized circuits of different lengths. So the purpose for this, by the way, is I think this makes more sense if I tell you the outcome we're going for. At the end of the day, we want to create a circuit that basically gives us our success probability So that is just the number of times our circuit gives all zeros divided by the total number of runs, right? So for example, if we did 1,000, we only get 980 success, then we're going to give the success probability as 980 over 1,000. On the x-axis, though, we're going to want circuit length. And we'll see how, for these two different computers, different lengths of circuits lead to more or less error. Now, from the previous Zoom poll, you should expect that these lines will roughly go down, right? Because a longer circuit leads to more error, therefore lower success probability. So this is the result we're going for, is some graph that looks like this. And we'll think a little bit about why it looks exactly how it does. So what we'll do here is we'll use our randomized benchmarking sequence function to give us a whole bunch of circuits whose lengths are between 1 and 200. So this x-axis here is going to run from 1 to 200 with a couple of points in between. Okay, step 3 then is going to be to run all of these circuits, crucially using the noise model, right? This would not be very interesting if we didn't have a noise model. We have to make sure that we incorporate that. And then we have some other stuff here that just gets the result. You should be familiar with these lines. And then all that we're going to want is the number of times we got all zeros, because that's the result we're expecting. Any other result is wrong. And then step 4, we're going to use some plotting functions to create that graph that I drew before. Okay, so with that said, let's go ahead and hop over to the IBM Quantum experience. Just give me 1 second to switch over, and we'll see exactly how this works on there. Okay. So hopefully everyone can see my screen. Please let me know if the text is too small. I can increase the zoom a little bit if you want. Okay, so there's a little bit of an introduction here, which I already generally went over. We're going to do some importing first up, as we often start off with. So here we are using our usual imports, right? We've seen all of these before. Zoom in a little bit, sure. We'll do that. Perfect, okay. Yes, so these are the usual imports that we have. The only thing that might look a little bit different is this bottom one here, provider equals IBM Q load account. If you're running this on the IBM Quantum experience, this will just work, because in the IBM Quantum experience, you're already logged in. If you've been running this on your local computer using some other technology, you will have to specify your token, which I won't go over here, but you can probably figure it out. It's pretty straightforward. You just need to look up how to log in using Qiskit. For me, though, because I'm on the IBM Quantum experience, this is all I need. This is going to log me in and allow me to access IBM's quantum computers. So the reason we haven't had to do this in the past is because we've just been using the simulator. You don't need to log in to use the simulator. But today, we're going to be using the actual quantum computers to get our noise models. And to get those quantum computers, we need to log in. Okay, so I will go ahead and run that. So I guess, yeah, we've used Jupyter Notebooks quite a bit now, but you click the cell you want to run, you click the run button, and then when this turns into a number, we're good to go. Next up are a couple of new imports, right? So noise model we haven't seen before, but hopefully you have some idea of what that does. It lets our simulator simulate the noise of a real quantum computer. And then we get this randomized benchmarking function. Okay, so we're just going to call that RB. And then we're going to use matplotlib to create that nice graph at the end of this notebook. So we'll go ahead and run that. All right, so next we'll go ahead and do the steps of randomized benchmarking, or RB, step by step. Now, I already went over this in the slides, but I will hopefully go over them in a little bit more detail and a little bit slower here. Step 1, as I said, is to get the noise models, right? So for us, we're going to be comparing Belem and Yorktown. And so in this cell, we are going to get the noise models from Belem and Yorktown. In order to do that, we're first going to get the quantum computer itself. So in this case, I'm using provider, which already knows I'm logged in, .getBackend. So notice this is very similar to air.getBackend, which we used to use for the simulator. But now, because we're accessing a real quantum computer, we're going to use our logged in provider. And then with that quantum computer, we're going to create our noise model. So in order to do that, we do noise model dot from backend, then we give it whatever backend we want. Okay, so that is how we create our noise model. We're going to do the same thing for Yorktown. So we use provider.getBackend. And then here to get the noise model, we're going to use that same syntax noise model dot from. So just noise model dot from backend. And then I pass in this time my Yorktown backend. Just like that. Okay, so if I run this, I am going to load in, again, all of that knowledge that IBM has about the various errors that occur on Belem and Yorktown. Cool, so far so good. Let's scroll down a bit and go on to step 2 now. Step 2 is to create these random circuits, right? So each of these circuits is going to be generated randomly by Qiskit. All we know about them is that they will be identity, or they should be identity, right? Okay, if you think back to the slides, the 2 arguments that we had to pass into this randomized benchmarking sequence were the length of circuits we wanted, and then this thing called the Qubit pattern, which I didn't talk too much more about. So let's first do the lengths. This one is more straightforward to understand. We're given the lengths that we want in a comment here. So as I said, we're just picking some good sample points between 1 and 200. Right, so this is going to tell it, create us a circuit of length 1. Now, again, this is not exactly 1 gate. It's just kind of a rough measure for quantum circuit length. So yeah, length 1, something that's roughly length 5, roughly length 10, so on and so on and so on, all the way up to 200. Okay, and this is going to let us fill out that x-axis of the graph we're going for. Now, this Qubit pattern thing is a little bit weird, so I'll just give you the syntax for it. It's a double array, and then we're going to give it the number of qubits we want, but we're going to specify it like this. So we're going to do all of our simulations on 3 qubits, but instead of just giving it a number 3, we're going to do it this way. I won't go into the reasoning for that. I guess high level, though, is just that this actually provides more flexibility than what we're using it for. For our case, though, just this for a 3-qubit pattern is sufficient. Okay, so then we have this call where we are going to get our circuits. This second argument here, remember, we don't care about. That's why it's just an underscore. We're just going to forget it exists. And then we call our circuit randomized benchmarking sequence. Length vector is going to be this lengths thing. And then the RB pattern, RB pattern is going to be pattern. Just like that. Okay, so let's go ahead and run this. We won't see anything yet, but the next step I'm going to take is to explore some of these circuits. So this particular cell, by the way, takes, well, actually, that was pretty fast. This one can take a little while to execute because, you know, one of the circuits it's generating is like, you know, more than 200 random gates long, right? And so it might take a while. I know that I am running up on time here. I do apologize for that. But I am just going to finish off this notebook. It should take probably an extra 5 to 10 minutes, and then we'll go into optional content as usual. And this whole thing is recorded if you can't stay. Okay, so once I have my circuits, I'm first going to explore this a little bit, see what some of them look like. Now, as I very briefly mentioned in the slides, this RB circs thing that it returns to you is actually a 2D array. We're just going to leave the first index as 0 all the time. The reason for this, if you are curious, is that you can ask it to generate using different seeds, right? So for example, we're asking it to generate circuits of these lengths once. That's the default. But you could tell it, hey, give me 100 trials of all these various lengths. And then if you did that, this first index would let you choose which trial. And then the second index lets you choose which circuit. In our case, there's only one trial, so we're always going to use index 0. And then let's look at some of these circuits, shall we? So the first circuit in this array is the one where we specified length 1. Again, that does not literally mean that there's going to be one gate, but it's a rough proxy for how long this circuit should be. So let's see what it looks like. Okay, so as you can see here, definitely not one gate, right? This thing looks actually pretty complicated. But this is a 3-qubit random circuit. And if you actually took the time to work out what all of these different gates do, you would see that it should be identity. Now, obviously, we're not going to do that. This is a complicated circuit. You'll just have to trust us here. Somebody asks, are all of these palindromic sequences? Not necessarily. They are inverted, though. So you'll notice that this has a barrier right here, right? Which, again, doesn't mean anything, but it's a visual. Basically, what it does is it randomly generates the first half, and then it computes the inverse and puts it in the second half. Sometimes the second half is not exactly just the mirror image of the first half, though. And that's just a linear algebra thing. Okay, so yeah, this circuit, like I said, take it for just on faith, I guess, that this thing should be identity. Yeah, people asking for the access code. Sorry, I keep forgetting to throw it on my screen here. 8437. Okay. Yes, where was I? Okay, so this is the circuit of length 1, right? So you can imagine if this thing is what it calls length 1, imagine how massive the length 200 circuit is going to be, right? We'll just take a look at a few more, though. So for example, the length 5 circuit. Again, I'm just stepping up in this lengths vector I gave it, right? So we'll go 1, 5, 10, 20, 50, so on and so on. This was the length 1 circuit. This is going to be the length 5 circuit now. And as you can see, this is getting quite long, right? And so again, just to explain a little bit what's going on here with all the barriers, what you're seeing is it generates five initial pieces. So here's the first piece, barrier, second piece, barrier, third piece, barrier, fourth piece, barrier, fifth piece, barrier. And then the sixth piece here is the inverse of all of those first 5, right? So it's gone ahead and just computed that for you. So each of the sort of individual pieces of this circuit, each of the circuits in between the barriers is one sort of random unit, right? And then the last one is the inverse to make sure that everything should come back to 0, 0. The 200 one would probably take like a full minute just to display on my screen. So I probably won't, but you can. It shouldn't, like, it's not so bad that it would break your computer. You can totally try it. It's just one heck of a circuit, though. And now hopefully you can see why we didn't want you to make these things by hand. This is why Qiskit has a function for this. Okay, so we've got this big array of circuits, right? And all of them should be identity. And as we increase this number here, they get longer and longer and longer. That's really the point I want to make here. But yeah, it can be fun to look through these circuits and look at the massive ones. Okay, steps 3 and 4 should be a little bit more straightforward. In my opinion, the most difficult part of this benchmarking was to explain those circuits, even though I guess I didn't explain them in too much detail. But yeah, now that we have those circuits, now it is down to Python programming ability to do what we want, right? We have all these circuits, and we know that conceptually what we want to do is go through every single circuit and execute it on both computers. Now we just got to make some code for that, right? Generally speaking, in programming, whenever you have some sentence that starts off with for every x, for every circuit, we want to do blah, 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 you're going to use a for loop. And so here we're going to go through a for loop of all 11 of our different circuit lengths. So there were 11 of them, 1, 5, 10, so on and so on. And for each one, we're going to run the circuit using the Belem noise model and then run it using the Yorktown model. Now, I'm just going to go ahead and fill in some results here. The job is already written for us. We're going to execute rbcircs. Remember, this first index is always 0 because we've only run one trial. I is going to give us the particular circuit. We're going to run it on a simulator for the backend. So notice up here, backend is defined as the simulator. But to make it look realistic, we're going to use the noise model for Belem, right? And then hanging off the side of the screen here, it just says the number of shots is SH. So notice here, by the way, this is a big number, 1024 by 256. We're taking a lot of shots here just to make sure we get a good average for our result. Okay, a couple of questions here. Could I explain these two lines? Yes. So these are going to be the number, so count 000 Belem is going to be the number of times we achieve 000 on Belem. Now, why is it an array? So this np.zeros 11 is going to generate an array of length 11 where all of the values start as 0. That's all. And what we're going to store is that every index in that array, it's going to store the number of times we saw 000 given an array of that length, or sorry, given a circuit of that length, right? So for example, the first element of this will be the number of times we achieve 000 given the length 1 circuit on Belem. The next index will be the number of times we achieve 000 on a length 5 circuit on Belem, and so on and so on. And then we do the same thing for Yorktown as well. So we know for all of these that we're going to do a total of whatever this number is, trials. And then we expect to achieve 000 slightly less than that, right? And exactly what that ratio is will give us the chance of success. So somebody asked in the chat, will my Jupyter notebook be shared after the session? Yes, absolutely. I'll send out an announcement with it. It should be an attachment on the announcement email. Okay, so hopefully that helps clear up some of the questions about the setup here. So yeah, these are really just creating arrays of length 11 with all zeros to begin with, and then we're going to set those counts to be the number of times we succeed in each case. Okay, so let's hop down here again. Once we execute our circuit using the Belem noise model, we're going to get results. So this looks the same as you're used to. We just do job.result. And then this line here to get the counts is also exactly what you're used to. We're going to do results Belem dot get counts, I think is what this looks like. Yes. Again, don't worry too much about memorizing exactly how this code looks. What I'm more concerned about is making sure you understand what it does, right? That we're sort of simulating all these different circuits and we're seeing how bad the error is given the length of the circuit. And then the last line here is where we use that count 000 Belem thing. So the number at index I is going to be equal to the number of times we got 000. So this syntax here is just asking from that simulation, how many times did we get 000 out of our 1,000 times 200 trials. The backend we're using in the execute command is the simulator, but we've given it a noise model to simulate Belem. Okay, now Yorktown is going to be pretty much the same. So the job is going to look the same. Execute rbcircs. First index is always 0. Second index is going to give us the circuit. We're still going to use the same backend, right? We're still using the simulator, but we're going to give it a different noise model. So we're going to use noise model Yorktown in this case. And then the number of shots is going to be equal to this SH value that we had above as well. All this code is the exact same, but now I'm going to replace it all with Yorktown. Get counts. Okay. And then we're going to fill up this count 000 array. And then on every iteration, we're just going to get it to print out some progress so we know how fast it's going. And that's it. So just to recap here again, for every one of these random circuits, we're going to run it on both Belem and Yorktown. We're going to see how many times it succeeds, which our definition of success here is just that we start in the 000 state and we should end in the 000 state. So let me go ahead and click run. This one will take a little while to execute because, well, as you could see, it has to simulate some very, very long circuits, right? So this is going to tick through. It shouldn't actually take too long though. This would take much longer if you ran it on real quantum computers. This is why we're using a simulator. Simulators can be very nice. So somebody asks, is the first index of RB circs the pattern array index? That's a great guess. It's not. It is the index of the trial. So in this case, we're asking it to only generate one circuit of each length. You can ask this function to generate 100 circuits of each length. And in that case, the first index would tell you which of those 100. Yeah. The pattern array thing is, well, I'm happy to talk about what it is in the optional content. I don't actually think it's all that important though. It's just kind of a technical detail. Okay, so we're done. It has gone ahead and executed all of these different circuits, which honestly, if you ask me, is really impressive. Remember, we're doing like, whatever this is, 1,000, 10,000, 100,000 plus trials on every single circuit on both of these different noise models. It's really remarkable how fast this thing is. But anyway, okay, so we're done. Now the final step is to create this nice graph I promised you. I'm not going to explain exactly how this works. It's just matplotlib. That's not really the point of this course. I more just want you to see what the graph looks like. So I'm going to run this, and then we're going to spend some time talking about it. All right. So I'm going to give you maybe just like a couple of seconds here to look at this graph for yourself. Start thinking about what trends you see, if these trends match up with your expectations, and then I will talk about it in just a minute. Okay, so I'm going to start off with pointing out, I guess, the more obvious trends, right? Number one, as we're expecting, there's a negative slope, right? With the smaller circuits, we achieve much higher probability of success. Though note, this goes back to what I said before, Yorktown only has like a 70% chance of success, even for that length one circuit, right? And then of course, it just gets worse from there. So yeah, quantum computers right now have pretty high error rates. But anyway, that generally makes sense that it should go down. The other thing we observe is that Belem generally, at least until very large circuits, generally has a higher probability of success than Yorktown, which again, we were expecting. Remember, one of our Zoom poll questions was, which of these will have fewer errors? Belem has fewer errors, therefore it has a higher probability of success. Now, the last thing I want to point out here is where this graph settles down. If you were very observant, you might have noticed that the probability down here is not 0, right? It ends off at some value. It appears to be just above 0.1, right? So why is it? Yeah, somebody asks, is greater length success rate of Yorktown, is it actually increasing? It shouldn't be. That might be some experimental fluctuation, but these should generally go down exponentially, and they will hit a certain asymptote. So does anybody have ideas about what this asymptote is? Why doesn't the probability of success just go to 0 as their circuit gets longer? Any thoughts on that? So someone says, if there is complete noise, even then, sometimes it would give a correct answer. Exactly. And a few other people are saying similar things. So remember, we have a 3-qubit system here. I didn't emphasize that too much, but all of our circuits were 3 qubits, right? And with 3 qubits, there are 8 possible measurement results, right? You can get all zeros, you can get 001, 011, 111, so on and so on. There's 8 possible results. And even if you had total randomness, 1 out of 8 of those is always going to be 000. And we're going to count that as a success, right? And so the asymptote this is hitting down here should be around 0.125, which is 1/8. If we had done circuits with more qubits, of course, the asymptote would be lower because the chance of success from a purely random output would be lower. Okay, cool. So we already went over this discussion point. This is the reminder from the slides that we already saw Belem, at least in theory, should have a lower error rate. And indeed, it does have a higher success chance. Okay. So there's two last discussion points here, and then I promise I will be done, or at least done the non-optional stuff. And I think, honestly, we already kind of talked about this. Gate fidelity, I mentioned offhand, is one metric you'll hear a lot talked about in the literature. I won't go into exactly how to derive it, but it is very closely related to the exponential decay constant on these graphs. So just by looking at this graph, you would be able to tell what the gate fidelity is. Oh yeah, this is a great analogy. Someone says an analogy for this, why the asymptote is not zero. Even a clock that stands still will be correct 2 times in 24 hours. I love that. That's awesome. Okay, and then the second discussion point here is on connectivity. I think we already gave this a good treatment in the slides where, yes, Belem is less connected than Yorktown, but it's able to achieve better error rates. And so there's always a trade-off there. Okay, that brings us to the end of the optional content. So I'm going to, end of the required content. So I'm going to throw up the post-lab Zoom poll here to see how everyone is now feeling about randomized benchmarking. And as people are filling that out, so just in the meantime, I will briefly mention what else is in this notebook. There are 4 challenge problems. I'm not going to talk about them in the lab, but certainly if you are interested and you want to learn more about this stuff, these are all great practice. And then, as always, we have some extra content. Specifically here, we talk a little bit about pulse programming, which is essentially, you can think of it as like, gate level programming is higher level, pulse level is like one step closer to the hardware. So if you're interested, feel free to read that, but totally optional. All right, so with that, as I said, that's the end of the required content. We will now flip over to optional content. Much like the last lab from before, I don't have any optional content prepared per se. So I am happy to sit around and answer questions basically for the next 15, 20 minutes. I know that there were some questions I didn't get to above in the chat. So if those people are still here, please feel free to just copy paste your question and I will go ahead and answer it now. Okay, so somebody says quantum volume again. I will give a quick description of that. Although, like I said, caveat here that I'm personally not super familiar with how the actual calculation works. My understanding of quantum volume is that it's supposed to be a more reliable metric for measuring the power of a quantum computer. Oftentimes, especially in sort of like popular science literature, and honestly, even when I talk about it, sometimes I fall into this trap of talking about the number of qubits as if it is the most important thing in the power of a quantum computer, right? But D-Wave is a great example of this, where having 2,000 qubits, in some sense of the word, is in many ways about as powerful, in some senses, as a 30-qubit computer from IBM, for example. And the reason for that is because D-Wave's qubits, maybe they have higher error rates, right? I don't actually know which of these is true, but maybe they have higher error rates. Maybe they have less connectivity. Maybe, I don't know, maybe there's more gates that you can do on an IBM computer than you could do on D-Wave, all that kind of stuff. And so quantum volume is something IBM came up with. It's supposed to be a single number that captures all of these different factors: the connectivity, the number of qubits, the error rates, the gates that you can perform, decoherence times, like all that stuff is packed into quantum volume. Now, there's some controversy about how exactly it should be calculated because the power of a quantum computer is subjective, but that's the general idea. It was meant to be a more accurate measure than just the number of qubits for how good a quantum computer is. Okay, so let's see. Somebody then asks, will the results derived from different quantum computers be different? If yes, then how can we decide which results are accurate or close to accurate? That's a great question. So a lot of the stuff we've been seeing here, like in this course, for example, we were finding Waldo, right? We already knew where he was. And so we could easily check and see, did our quantum computer come up with the right answer, right? In a lot of real world problems, though, that's not how it works. You don't know the answer and you're relying on the quantum computer to give you the correct answer. And so given all this error, how do you know if it gave you the correct answer? Especially, if you ran some crazy complicated algorithm on Yorktown and Belem, and they each gave you a different answer, how do you know which is right? There's a couple different answers. Number one is that for some problems, it's easy to check if the solution is correct, even though it can be hard to find a solution in the first place. So those kinds of problems tend to be nicer to work with, because if these two computers give you different results, you can easily check them, even if you weren't able to come up with those results on your own. If that's not the case, though, then you have to turn to this study of error mitigation, which is one of the things I talked about. And error mitigation basically looks at how can you take the flawed results of a computation and try to reverse engineer what errors occurred and therefore what the real answer should be. So you could try error mitigation techniques to see if you can sort of refine your answers. And then as sort of a last resort, if you do your error mitigation and you still see that they give different answers, then I would probably just rely on Belem because it's more accurate. It has fewer errors, right? That has a whole bunch of problems with it, though. You should really try and be more systematic than that. But generally speaking, that's how it would work. There's this whole branch of error mitigation is the study of how you take imperfect results and reverse engineer what you think the result should have been. And that's what you would do in this case. Okay, so somebody says, by the way, you also mentioned talking about quantum compilers a little bit. Yes, absolutely. So I think I already did a little piece on that right before our winter break, I believe. And well, I can either sort of give a similar presentation again, or I can try and expand on that. I think, well, yeah, I can do a little bit of an intro to it. So let me switch back to my tablet here. Just out of curiosity, how many people remember the stuff I talked about from before winter break? Like, is it worth me repeating that, or would that be repetitive? Repeat. Okay, cool. Sounds good. And actually, well, this is actually quite a good time to talk about it now that I think about it, because there is that little bit of extra content in the notebook about pulse programming, and quantum compilers are very closely related to pulse programming. So I will talk about that. Okay, so the high level of quantum compiling is to do with this whole chain going from program, like Python code that you write, down to actual atoms being flipped around and that kind of stuff. So over here at the top left, say, we have Qiskit, right? So this is Qiskit Python code. And usually in Qiskit, at least how I'm going to talk about it here, usually you're specifying some kind of circuit, right? So let's say that you use Qiskit and you specify some circuit that looks like, I don't know, this. Right, we got an entangled state being created, and then maybe we're going to C0 that with some other qubit down here. And then we're going to apply a Z gate, right? Just some random circuit. Okay. And then we're going to measure everything. All right. So Qiskit and Python, you're going to use that to define this circuit. At the end of the day, depending on what your quantum hardware is, you need some way of actually doing these gates, right? And so the example I'll talk about, just because it's, again, what I'm familiar with, is atoms, when you use atoms and electron orbitals as your qubits. So the way that gates are done with electrons is with laser pulses, right? And each pulse, there's a whole bunch of physics behind this, which is very interesting. And honestly, I don't know it. I would love to learn it. Laser physics is a wild field of study just on its own. But suffice it to say that when you have a particular laser, I'm going to do my best to draw something here, pointed at some atom, even though, yes, I'm aware atoms don't actually look like this, but we'll just draw it that way. You have some laser pointed at an atom, right? This laser has a couple of different parameters. It has frequency, for example, right? And so frequency is just the oscillation of that wavelength of light. There is the duration, which is just how long you turn on the laser. Then there's also something called phase, which you'll be familiar with if you've taken some electromagnetism courses. Otherwise, maybe not so much. But basically, light is also called electromagnetic radiation. And the reason it's called that is because if you shoot a beam of light in this direction, it actually has an electric field that goes like this, and then it has a magnetic field that's perpendicular. So it's going to be hard for me to draw here, but it's kind of, if one is going up and down, the other is going side to side, right? And the distance between the peak of the electric and the peak of the magnetic waves is called the phase. So they can be perfectly aligned, in which case your laser is what we call in phase, or they can start to be apart from each other, and that's something we call dephased. So not super important, but basically we have all of these different numbers associated with a laser. And so, what's an example? If I want to do an X gate, right? An X gate is sort of the most standard example here. I would assign my frequency to be, 10 megahertz, for example. The duration would be pi divided by 10 megahertz. And I won't go into exactly why this is or how to derive it. And the phase would be 0. So it's perfectly in phase, right? And this would go ahead and do an X gate for you. Now you can change any of these numbers, right? Each of them is just like a little dial on its own for adjusting various parameters on the laser. And you can tune them to do different kinds of gates. But somehow you need to go from this circuit up here down to this sequence of pulses, right? So I guess this is the last thing to mention. When you're doing a quantum computation, chances are you're going to have multiple lasers, each with different parameters, and they're doing pulses in sequence, right? So maybe I have one laser over here, it'll turn on first, and then I prepare a second laser with different parameters that will turn on second. And so often we'll talk of pulse sequences, which is just, turning on the lasers in sequence. And that is what it actually looks like to do a quantum computation on atoms, is you're shining these lasers, the electrons are bouncing up and down between orbitals, and that's how you make magic happen, right? So there's a couple of different ways you can do quantum compilation. The first one I sort of alluded to here is that you can try to figure out the best laser parameters for each gate that you want to use, right? So if I wanted to compile this circuit here, we see that I use H gates, C naught gates, and Z gates. So I would have to go away and figure out what parameters I need for an H gate, a Z gate, and a C naught, right? And each of those would have some parameters that I have to calculate, and then I have to go and do some experiments to figure them out, whatever. I can find these values. And so this method of compilation is fairly straightforward. Unfortunately, though, this is fairly straightforward because it turns out that any 1 qubit gate can be done with a single laser pulse. So we can straight up just solve for the values of H and the values of Z. What is not straightforward at all is 2 qubit gates, like a C naught. So something like a C naught, we know how to do it in some sense, but there are actually many different ways you can do a C naught gate. There's many different combinations of pulses. There's no unique solution, right? So for these 1 qubit gates, you can literally just solve, it's like a math equation, and you can figure out what these parameters should be. But for these 2 qubit gates, there's lots of different solutions, And it's often not at all clear which one is going to be the best, right? Maybe some of them take more laser pulses, but they have a lower error rate. Or maybe some of them take a longer total duration, right? You have to leave the lasers on for longer, but it's going to give you a lower error rate, right? So again, there's all these trade-offs. And so what often happens is there's going to be many different ways you could do CNOT. And then your compiler has to somehow figure out which of those different ways is best for this particular circuit. And that's where a lot of the active research is, sort of figuring out how you decide which two qubit implementations will be best for certain scenarios. I just noticed there's a couple of questions. Each laser has a fixed frequency, or is it tunable to some degree? So yeah, that's a detail I sort of skimmed over. Each of these lasers is tunable, and you can actually change these parameters continuously in time. So sometimes you'll hear people talk about something called pulse shaping, which would be, for example, one laser, the frequency could have a continuous distribution. So if the x-axis is time here, and maybe I'm turning this laser on for 1 second, the frequency might do something like this. You can actually like tune it continuously over time. So I sort of glanced over that detail. These don't have to be just fixed numbers. They could be functions. But it's still easy to solve for them in the 1 qubit case, much harder in the 2 qubit case. Are we working on each electron, or do we just shoot lasers on a bunch of them? So these lasers are very accurate. They're accurate enough that you can shine them on a single atom, but you can't target an individual electron. That would be way too hard. And so often what we do is we will pick atoms that have, well, to be honest, this is one area that I am not as familiar with. So take what I'm about to say with a grain of salt. But we'll pick atoms that have nice properties where when you shine the laser on them, even though it will affect all of the different electrons, one of them will be relatively independent from the rest. And I'm sure there's a whole bunch of chemistry and physics behind why some atoms have more independent electrons than the others. But that's the general idea. So yes, the lasers affect all the different electrons, but we only use one of them as the qubit. Yeah, I know, it is super impressive. Like the study of how you do, this is called photonics, by the way, the study of very accurate lasers. And by the way, accuracy means both shining it at a particular location, but also, you know, if me as a theorist, if I give one of my experimental like partners a particular function that I want them to do, it's also up to a photonics team to figure out how do you make a physical laser follow that function as closely as possible, right? And so that's a whole other area of physics that you can get into. Okay, so let's see, where else? Oh yeah, so the other thing that I would mention on this is this is one problem, right? And this is maybe the most obvious way of doing quantum compilation is by translating each gate to an equivalent set of pulses. The issue with that is, again, these 2 qubit gates. Okay, there is another approach to quantum compilation, which is a somewhat separate but sort of related area of research. And that is, if I gave you a circuit like this, right? Whoops, what am I doing here? So if I gave you some circuit, it could be that our particular quantum computer, whatever it is, so say it's an atom-based quantum computer, it could be that our particular quantum computer has one laser that can do maybe this, right? Maybe there's one laser you can do, you can create one set of parameters you can create that will do this kind of double CNOT pattern, right? So that's not traditionally a gate that we think about, but maybe for our particular setup of lasers, we can do that efficiently, right? And so then what we would want to do is we would want to try and restructure our circuit to use as many of these native gates as we possibly can, right? Even if they're not the gates that we're used to talking about. Maybe for our particular quantum computer, it's really hard to do a Hadamard gate. And so we would want to break this up into, I don't know, this would be a really weird computer, but say it's easier to do CNOTs than Hadamard gates for some reason, right? Then you would want to break the Hadamard into CNOTs somehow. And so that's kind of a a transformation step that's called transpiling. And I think we actually talked about this super, super briefly in one of our previous labs. Transpiling is staying at the circuit level, but replacing some of your gates with different sets of gates to make it more suitable for your particular computer, right? And that might involve some custom gates that only your particular computer can do efficiently, like a double CNOT, or it could be something way weirder, right? So the ultimate dream of compilation is to have both of these things operating in tandem. First, you would transpile your circuit to a set of nice gates for your particular implementation, and then you would use some kind of table like this to figure out which pulses are going to do that particular circuit. But each of these independently right now are hard problems and the subjects of many areas of research. Okay, so hopefully that was a good kind of overview. Let me see. So somebody asks, if I were to do a master's in quantum computing, will it have to be in photonics? No, not at all. Photonics is one potential area of research. If you want to really think a lot about these lasers and how they affect atoms, it would be more on the physics side. There's a whole bunch of areas of research that are more on the computer sciencey side, right? So for example, well, all of these things really. This one here, sort of going from gates to parameters, is actually more of a numerical optimization problem, right? Because a lot of the times to solve for these 2-qubit gates, you can't do it by hand, that's for sure. So you have to get a computer to do it. And getting computers to solve difficult math equations is generally called numerical computing or numerical optimization. And then this one here, this transpiling stuff, is more of a theoretical computer science question. How do we identify, how do we identify particular gate sequences that can be replaced by better ones? What are the heuristics therein? So on and so on. So both of these, I would say, are more CS related. Photonics would be more physics related, probably. But there's a lot of variance out there too. So somebody asks, does the shooting of a pulse disturb the quantum state in some cases? Yes, but usually you want it to, right? Usually when you're shooting a pulse at an atom, you want it to do an X gate or an H gate or something like that. It might not do that gate perfectly, and that's what we would call a gate error, like we just learned. But usually you want it to disturb the atom in some way. Yeah. Oh yeah, so somebody's asking, if the atoms are constantly moving, how do you target them? So they're not constantly moving. And there's a couple of ways that we do that. Again, this is venturing a little bit more into the physics. But step one is you want to get the atoms to be very cold, right? Because again, going back to this idea of temperature as kinetic energy, if your atoms are very cold, they're going to not move around as fast, right? Which will make them easier to target. The other thing we use, though, which I think is the more important point, is something called optical tweezers. So optical tweezers, I would definitely encourage you to look up how they work, because it's actually quite fascinating. I had no idea that light works in this way, but it turns out you can create a laser beam that sort of has this like Gaussian energy distribution, right? Where there's kind of like a high energy point in the middle of the laser, and the energy dissipates as the laser goes out, which is wild to me that you can create a laser beam with such precision. But turns out you can do this. And if you accept that fact, then you can engineer something where the atom is sort of pushed into the middle of that laser beam, where it's highest energy. And whenever it tries to move out because of thermal vibrations, the high energy in the middle of that laser beam pulls it back to the middle. And so what you can do is, you have one of these lasers shining maybe straight down. That means that the atom can only move up and down. Then you just need a second laser that holds it in a vertical orientation. And at least in theory, your atom is going to be roughly in the same position at all times, because these two lasers are going to hold it there. Then you can go ahead and set up your pulse lasers. I know there's a lot of lasers in this setup, but you can set up your pulse lasers to target that particular location. And there's a very high probability that your atom will be there when you do your pulse. Yes, my background is CS. I fall into the category of people who think that physics is very fascinating, but would rather spend my time studying and sort of getting into the weeds of computer science. So, all right. I think I hit, well, actually, there were probably some questions from before I got into quantum compilation. The required section of the lab is over. Yes, I'm just riffing on optional stuff now. Okay, let's see. Yeah, so if anybody else has questions, feel free to, I think, post them on Piazza. I've already gone for a little bit of time here. So I think I will wrap it up. But thank you for everyone who stuck it out right until the end. I hope that was somewhat interesting. Yeah, as a reminder, you can find this recording. It'll be posted very soon afterwards. And if you have any more questions, feel free to go ahead and post them on Piazza. Okay, thank you, everyone, and we will see you later. Bye.